All right, so let's take a look at a first example of surface area. So find the surface area of the portion of z equals 2 minus x minus y over x squared plus y squared less than or equal to 1 in the first quadrant. So that was last part there is describing our region R. So let's go ahead and draw R in the xy plane. So we've got our little xy. And what we see is we've got that x squared plus y squared less than or equal to 1. Well, that's just our unit circle, and it says we only want it in the first quadrant. So we're just going to go from 1 to 1, and we've got our little quarter circle here, and then it would be fully filled in since we want less than or equal to 1. So this is our region R, so we can take a look at describing that region. We could say have y go from 0 up to that upper half semicircle, which would be square root 1 minus x squared. Right, we're just taking this and solving the equality for y, and then taking the positive for the upper half semicircle. And then we would have x goes from 0 over to 1. And then what we're going to take a look at now is putting that in our surface area formula. So to remember our surface area formula, sorry about that, was surface area was that double integral over R of the square root of 1 plus z sub x squared plus z sub y squared. And then we're going to do that with respect to area. So let's actually set that integral up. So our x bounds, our outer bounds, would go from 0 to 1. Our y bounds go from 0 to square root 1 minus x squared. And you'll notice we're going to need, let's do a little side work over here. We need z sub x and we need z sub y, so those partial derivatives. So z sub x, well, the derivative of 2 goes to 0, negative x with respect to x will go to negative 1, and then negative y with respect to x will also go to 0. So then we'll have z sub y is also negative 1. We're really just looking at that negative y, and its derivative will be negative 1. So this will look pretty nice here. We're just going to have the square root of 1 plus negative 1 squared plus negative 1 squared. And then this would be, we chose the order dy is on the inside, and then dx. Move this line out of the way. So simplifying there then, we've got this integral 0 to 1, 0 to square root 1 minus x squared, and then we've got really just the square root of 3 on the inside. And we've got that dy dx. Okay, so now really all we have to do is evaluate this integral. Taking a look at that integral, at this point now we could decide however we want to evaluate this. And one thing that we might have noticed even from the beginning that is really interesting is this region R is very easy to represent in polar coordinates, because it's circular in nature. So we would have that R is just going to go from 0 over to 1, right? We've got R goes from 0 to 1. And then theta just makes a quarter turn. So it goes from 0 to pi over 2. So it goes to that 90-degree angle. So, and it's going to be pretty easy to make this change because notice the integrand, the thing on the inside, is just a constant. So when we sub in x equals our cosine theta and y is our sine theta, really we don't sub anything in because there's no x's and y's. So then we're going to have the integral, we'll have 0 to pi over 2, the integral 0 to 1, and then we're going to have square root 3, and then don't forget your r, dr, d theta. So we've got that change of coordinate scale factor there for the r dr d theta. All right, so now we can take a look at trying to simplify this. So we're going to do our integral with respect to r. So we're going to get the integral 0 to pi over 2. It's just a square root 3r, so it's going to become square root 3 over 2r squared, which then we can put in that 0 and 1 evaluation, and then this is still d theta. So then we're going to get the integral 0 to pi over 2. We're going to plug in 1 and just get square root 3 over 2. And then subtract off plugging in 0, which just gives 0. So we just have square root 3 over 2 as our integrand. So when we integrate that d theta, we're just going to get square root 3 over 2 theta, which we're going to evaluate from 0 to pi over 2. Which when we plug in pi over 2, we're really going to get square root 3 over 4 times pi, because the 1/2 times 1/2 is 1/4, and then plugging in 0 just gives 0, so this would just be minus 0. So our final answer is square root 3 over 4 pi. So that's the surface area of our solid that we would get from taking a look at z minus or equals 2 minus x minus y on this over this circular domain region. So notice this is actually a portion of a plane that we're taking a look at. So that's our answer for that one is square root 3 over 4 pi.